take a look at another example. In this case we have a motor winding a cable, and we're told that the velocity of the cable is equal to 3 feet per second, and we're asked to determine the power supplied by the motor. So we're looking for power, and that's going to be force times velocity. So I need to figure out what is the tension in this cable right here. So we're also given that the weight of this load is 100 pounds and the efficiency of the motor is 0.8. So we have to keep in mind that the power of the motor is going to equal the power found from the tension. That's basically the power output divided by the efficiency, because remember, efficiency is power out divided by power in. And the motor is going to be the input power, and then whatever the tension is doing is the output power. Alright, so if I think of a force diagram acting on the load, I'm going to have 100 pounds down. The tension is up. Now this is a different tension. I'm going to call it T2. This is the tension here, which is also tension here and here. And so T2 minus 100 pounds equals MA. But if I'm pulling at a constant speed of 3 feet per second, even though that's right here, it's constant. That means the speed of this cable is also constant, which means I'm lifting the load with a constant speed, which means the acceleration is equal to 0. So T2 is equal to 100 pounds. Now if I do a force diagram on the pulley at B, and we neglect the mass of the pulleys, but that doesn't mean I can't do a force diagram on it. I'm going to have T2 up, and T down. And so 2 T2 minus T equals mass times acceleration, but the mass is 0, so T is equal to 2 T2. So that means that the force of the cable here is 200 pounds. The velocity is 3 feet per second, so the power is 600 pound-feet per second, and then I divide that by the efficiency, which is 0.8, and that will yield 750 pound-feet per second. Okay, here's another example. I have a four-wheel drive with a mass of 2.5 megagrams. So the mass is equal to 2,500 kilograms. That's the mass of the SUV. And the mass of the trailer is 1,500 kilograms. The traction wheels, the traction force developed by the wheels is 9 kilonewtons. And I want to determine the speed of the truck in 20 seconds. It starts from rest. So V initial is equal to 0, and we're looking for V20. And I am also interested in the tension here in the coupling at A. Alright, so the forward force, FD here, is the only force in the forward direction, and that's 9 kilonewtons. I'm going to look at impulse here. So I have 9 kilonewtons times 20 seconds. That's going to be the impulse. The initial momentum of the system is 4,000 kilograms times 0. So there's mv initial plus the integral of f dt. Of course, f is constant. And that will equal 4,000 kilograms times v final. So I end up with 180,000 newtons, that's a kilonewtons, 1,000 newtons, equals 4,000 kilograms times V final. And so V final equals 45. That should be newton seconds here. Meters per second. Keep in mind a newton is a kilogram meter per second squared. When I multiply that by seconds, I get kilograms meters per second. And then those kilograms left side, right side of the equation cancel, and I'm left with meters per second. In the second part, the tension in the coupling. In that case, the tension is the only force acting on the trailer, and so I would have 1,500 kilograms times 0 meters per second plus the tension times 20 seconds equals 1,500 kilograms times the velocity of the trailer, but of course the trailer is moving at the same velocity as the system. And so my tension would equal 1,500 kilograms, 45 meters per second over 20 seconds. So I have kilograms, meters per second over seconds, and that's going to be kilograms meters per second squared, which is a newton. That's a newton, so my units are correct, and I get 3375 newtons, or 3.375 kilonewtons. And it should be less than the total force pulling the system, because I'm only looking at the force pulling on the trailer. I could also look at the SUV. I have a backward force of the tension, Newton's third law, so 3,375 newtons back, a forward force of 9,000 newtons, and so that's 5,625 newtons. Multiply that by 20 seconds, and I should get the 2,500 kilograms times the 45 meters per second, the final momentum of the SUV. Let's check that out, and indeed both sides of the equation yield 112,500 newton seconds. That's the same on both sides, which it should be. Okay, our last example here is a very interesting example for several reasons. It's really a simple conservation of energy problem. I have no friction in this system. I have gravitational forces acting on both blocks, W1 and W2, but that's a conservative force. I have a spring acting on W1, also a conservative force. And so I don't need to worry about any work done by non-conservative forces. But the part that's interesting is the datum, because if I consider the center of mass of W1 to be somewhere in here, I'm going to make this the datum, starting point for W1. So this is y equal to 0. Now you'll notice that that's not the same as where W2 is. How far below is W2? I don't know. But the beauty of it is, it doesn't matter. I can make the datum for W2 different than the datum for W1. So this is y is equal to 0 for W2. Then as I look at energy, as W2 falls, it's going to lose gravitational potential energy. W1 is going to rise, it's going to gain gravitational potential energy. Alright, so how are we going to solve this problem? I'm going to start with an energy bar graph. I'm going to have a kinetic energy for W1, a kinetic energy for W2, a gravitational potential energy for W1, a gravitational potential energy for W2, and a spring potential energy because of the spring here. All of those energies are the combined energy of my system. Now if we go back to the problem, I know the weights of the two, I know the spring constant, I know the angle is 30 degrees. The system is released from rest, which tells me the kinetic energy is 0. So 1/2 mv squared, 0, 0. I've started both of them on purpose at my datum. I need to look at the spring. The spring is at the equilibrium position, so the potential energy for the spring also 0. So my initial energy bar graph, no bars. So this is the initial. As W2 falls and W1 rises, they're each going to have some kinetic energy. So I'm going to give 1 bar to W1, 2 bars to W2. W1 is going up, so it's going to pick up positive potential energy because it's rising. W2 is falling, so it's going to have negative potential energy. And the spring is stretching, so it's going to have positive potential energy. Because remember, the potential energy of a spring is 1/2 kx squared. Has to be positive. So notice I have 1, 2, 3, 4, 5 positive blocks. I need to have 5 negative blocks so that we equal 0. Next step, let's put energy equations with our energy bar graphs. I have 0 on the left. That's going to equal 1/2 mass 1, which is W1 over g, times the velocity of 1 squared, plus T2, that's 1/2 the weight 2 divided by g, because I have to use masses, not weights, times the velocity of 2, but the velocity of 2 is the same as the velocity of 1. The constraint of this chord requires that V1 equals V2, plus W1 times how far it rises. Now, let's assume that W2 falls a distance y. that means that W1 is going to move up a distance y along the incline, which then means it will rise in the y direction. This is y distance, same as this y. This distance then is y sine 30 degrees, which I'm just going to leave as theta. So W1 sine theta, that's the positive potential energy increase for W1. Now W2 is falling, so minus W2 times y. I need a y over here. W1 times y sine theta. And then finally, if I pull the block up the incline at distance y, I am stretching the spring at distance y from equilibrium. So plus 1/2 k y squared. And all of that's equal to 0. What was the question? How far will W2 fall before stopping? In the case of stopping, V1 equals V2 equals 0. And so I'll solve this equation knowing this term goes away and that term goes away. So the only unknown over here is y. Part 2, what is the velocity of W2 after it has fallen 1 foot? In that scenario, y is equal to 1 foot. V1 is the unknown, but it's the only unknown. So I can solve that equation then for V1. And that's how you solve that problem. Conservation of energy, critical issue, make the datum for W2 where you want it. Make the datum for W1 in a different location, a convenient location. They don't have to be the same place.